What is this? I'm certain most of you know this is a processor, more specifically an Intel Pentium 4.
And you also probably know that inside there are transistors, billions of them. But how are they actually hooked up? In what order are they placed? And how can a rock show you crucial information for modern day-to-day life? Well, today I'm not gonna answer any of those questions, and instead build an entire processor from scratch. I know it's been done a lot before by YouTubers like Ben Eater, Sebastian Lig and JDH, but I don't see any transistors. Where is the transistor in transistor logic? That's why I decided to build mine without any integrated circuits.
Just these NPN BJTs and resistors. First, a bit of planning.
Think of a simple resistor with connections to power and a probe. At some point, the voltage we measure has to transition to either 5 volts, 0 or something in between. In binary, we only want 0 and 5 volts. So what if instead of connecting the ground directly to the resistor, we add a switch? This way the output is controlled by the state of the switch. And since operating thousands of tiny switches by hand would require like 125 octopuses, we should use transistors, which are basically switches that can be controlled by another signal.
How do we make logic gates with just switches? Imagine this wire and a transistor. If we connect the base to a positive voltage, nothing will happen because a BJT needs current flow from the base to the emitter
For the circuit to close.
Let's add a resistor to the input. But we run into another problem. If we measure the voltage at the output, it is dangerously close to 0.
And if a lot of gates use it as an input,
It can cause the voltage to drop so low it becomes 0 instead of 1. That is because the transistor isn't in the correct mode. BJTs have 4 operating modes: forward active, reverse active, cutoff and saturation. We want to use the last 2 modes. For an efficient running, we need a ratio of at least 5. I decided to use a 1:10 ratio since they're easier to find, and now we can see above 2.5 volts even with 10 gates. Now we have one more problem to solve. Here we have a gate with power resistance of 22 kΩ and it draws 200 microamps. But if you look at the signal, it takes 3 microseconds to rise.
and for the next gate,
It takes 20 microseconds. The entire processor will have like 40 gates to pass through in total for each instruction. And if a single instruction takes 10 milliseconds, then we can't run the processor at a frequency higher than 100 Hz. With a tenth of the resistance, we can achieve 1 microsecond.
the downside of faster times,
Is a higher current, and current we can spare.
what happens if we add another transistor after this one? Neither of these transistors can pull the voltage down on their own. Only when both of the inputs are positive, the output is pulled down to 0.
Creating an inverted AND gate.
If we put the transistors in parallel instead of series, both of them can connect the output to the ground, creating an inverted OR gate.
Let's move on to the next component, the oscillator. This will control the clock signal that everything in the processor will run by, and we have 3 main paths: a quartz oscillator, a 555 timer, and a simple bistable oscillator.
You already know my opinion on integrated circuits,
And I can't find any oscillator with a small frequency. So the bistable it is. Here is the basic design I found on the internet, and I played around with the values
until
we achieved a 500 Hz clock. What's also nice about this is that by just increasing this resistance, we can slow it down to about 380 Hz. So let's change this to be in a range of 6 to 2 Hz for debugging, add a separate one with a permanent 500 Hz clock, and a button for manual stepping.
I also added an inverter at the end to filter the signal into a pure square wave, and an LED to see the signal without an oscilloscope.
Here we have the small 1 microfarad oscillator, the big 100 microfarad oscillator with the potentiometer, and at the end a simple button.
All connected by this pin bridge to select the output and pass it along to the NOT gate.
With the clock done, we can move to the first important component, the program counter.
What does it do? Think of it like the cursor in a debugger. After the processor executes an instruction, it jumps to the next one, and when it encounters an if, it has the ability to jump over it. Or in case of a loop, it can jump back to repeat the instructions. So this component has 2 jobs.
To count up on every clock cycle,
and to change the address to anything we want.
let's tackle the first one. To do this, we have to first remember the current number, and then add one and replace it. But how can we make transistors remember? With a latch. Here we have two NOR gates hooked up to each other. If we give a signal to one of them, the wire's state change, and it remains this way until we send the signal to the other one.
But we want to write binary data.
So as inputs, we will have a data line and the write line. When the write line is high, we want to store whatever is on the data line.
We want the top line to be active when writing a 1, so when both the data and the write lines are high.
And that can be handled by an AND gate.
The bottom line needs to be on when we want to write a 0.
So when the write is 1 and the data is 0. There is no gate for this specific outcome, but we can change the inputs. What if we invert the data signal? Well, the 0 we need becomes a 1. And the AND gate can solve this one too. This is called the data latch. If you remember the beginning of the video, the inverted logic gates take less transistors, so we can change this layout and use only NAND gates. There is also this little trick to use the first NAND gate as the inverter for the second one, sparing another transistor.
Now let's think about counting. Here are the binary signals for a 4-bit number. You might have noticed that all of them are just square waves, half as fast as the previous ones. Let's start with the data latch and hook up the clock signal. And we know that on every clock cycle we want to flip it, so let's hook up the inverted output as the data input. On paper this does work, but we are talking about transistors here, and this causes a feedback loop that just sets the output at a voltage between 0 and 5. How can we split the data latch in a way that changing the input doesn't immediately affect the output? We just add another one. Since on the negative clock cycle nothing happens, we can use it to store the data into the second latch. This way, on the rising edge, only the first one is updated, and on the falling edge, the second one is updated. Let's take a look again at the signals. We can also see that each one rises when the previous one falls. So we can copy this entire thing, and instead of using the clock as an input, we use the inverted data from the previous one. And just like that, the first part is done. For the second part, we have to somehow replace the signal with the input and force both data latches to remember the new value. For the latches, we can use an OR gate, so that both signals can activate them. And to replace the signal, let's create the truth table. As you can see, we only have 4 states that require a positive signal. So we can make a big OR gate for all 4, and then we can tackle each case individually. Now just like before, we can invert the zeros to make them ones and add an AND gate at the end. In the first case we need to negate the write and input signal. In the second case we need to invert the write signal. In the third one we invert the data. And in the last one we don't need to invert anything. To simplify the equation, we notice the common factors. These two can be brought to the front, and these two as well. Then these two additions will always equal 1, because if you have a value and its opposite, they can never be both 0, and multiplication by 1 is just redundant. Then to make this only with NAND gates, we can add a double inversion at the last gate. And the first inversion negates both inputs and changes the gate to an AND. After we add the selectors, we can spot 2 more optimizations. All of these require both the write signal and the inverted one. But since all of them use the same inverted signal, we can merge all the NOT gates into one and spread the output to the selectors. Then at this OR gate, we can also add a double negation and turn it into an AND gate. And this double negation we can just ignore, moving the NOT gate from the data to the right. But wait, we have the same case here, so again we can merge all of them and then spread the signal to where it's needed. The program counter is done. We can write any number at any time and it counts up by itself. And the best part about this is that it does it all in a single clock cycle, unlike some processors. Well, thank you all very much for watching, and good luck with your own projects.
Nope, I can't find them. Holy f***.